So I want to thank you all for coming. I think we're here to work on a really important topic, which is how to educate people to work with big data, and small data too, because that's interesting also. To prepare them for this new world where data is one of the resources we're all using all the time to make better decisions about real resources and how they should be managed and allocated. So our first speaker is Ruth Krumhansl. She's the director of the Oceans of Data Institute at the Education Development Center. And she's an expert in curriculum development, science teaching. And she's going to talk to us about preparing high school students for college and the world of big data. Ruth?
Hello, I'm really excited to be here. Now this mic is working, right? Yeah. Okay, all right, good. I don't have to stand next to that, it's too high anyways. I'm really excited to be here. This is a really important conference, and I want to thank the organizers for organizing it, the organizers at IBM and Syracuse University and University of Ottawa. It's just such a critical topic for us to be talking about, and I hope this is just one of many, many conversations that we have. I'm with the, as was mentioned, I'm with the Oceans of Data Institute. I was recently launched, so I'll be talking about that, and I'll also be talking about, I'm supposed to cover the pre-college part of educating that pipeline of people who will be tomorrow's data scientists, and I think citizens who reason with evidence. Now, I've found since I got into the field of big data that it involves many interdisciplinary conversations, and these conversations have been fascinating. It's such a new field that it involves, what it's doing is, it's new, but it's building on the deep understanding that we have from many, many different fields. And we have to have conversations, and we have to try to understand each other to form this new field. But sometimes, we're almost talking past each other. So in education, when we talk about schema, I think I figured out it's not the same thing that big data, the term schema always means. And we use terms like scaffolding and STEM and stuff like that isn't always meaningful to other people. So what I'm going to do is I'm going to talk to you first a little bit about where I'm coming from, where my world and where EDC is coming from, and how our world intersects with big data. So, and then, because I think that's important when you're beginning a conversation. So EDC. You may not have heard of it, but chances are it's impacted you. It's a large nonprofit, $200 million organization managing 250 projects around the world, more than 1,700 employees and projects on virtually every continent. And we've been around for a while. We've been around since 1956 when Gerald Zacharias from MIT started what was, EDC was actually, before EDC there were no education-oriented research and development organizations. And it started with PSSC physics. And this is a curriculum that was developed by the Physical Science Study Committee, started by Gerald Zacharias. And it was a curriculum that was very revolutionary for its time, because instead of emphasizing sort of memorization, it shifted the focus of physics education toward really focusing on fundamental concepts and investigating them. They had a whole series of films. They had a whole series of laboratory experiments that used simple materials and so forth. And it really revolutionized physics teaching even to this day. There's in social studies, another one of the sort of groundbreaking education projects was Man, A Course of Study, MACOS, which maybe some of you have heard of. And this focused around looking at the entire lifespan of human beings and looking at the social relationships that they had and so forth. And again, this was very revolutionary for its time. It actually ended up being quite controversial, one of the first sort of forays into the intersection between politics and education. And then elementary science study was another big project, which was one of the first that really, really changed the way science was taught in elementary school and into a much more hands-on, inquiry-oriented enterprise where students were really, really investigating things instead of just sort of following steps and so forth. So an innovator, and EDC since then has grown tremendously. We have projects all over the world. These photos are all relate to individual projects that we've been involved with. And then this is the earth scientist perspective. I am a geologist, that's my background. And to me, the earth is, and actually I think my background lends itself pretty well to the big data world. Because basically what the geologist thinks is the earth is basically one big, complex, unstructured data set that we have to try to mine. We have to figure out what to look at, how to look at it, and it took 100 years of observations and analyses and so forth to figure out things like plate tectonics from all of these individual observations. And I'll talk to you a little bit about my background. My history with data, judging from the yellow color of these things, I probably should have put my ancient history with data, and I have done stuff since then. But this is going way back. I worked initially in oil exploration, and that was way back, kind of in the age of punch cards, remember those and things. And basically, what they would do is they would give us, you can see on the left, this is 6 feet tall, and these are section lines in here, like a mile by a mile. And we would get these maps that had, and this is a section of, it's an area of Oklahoma. And we would get these maps that had, imprinted on them all the wells that were drilled. And you can see that some of these have dots on them. Those are the ones that that produced oil. And then there are also some other ones that don't have dots on them. And they were drilled, but they didn't produce oil. And actually, where you didn't find oil, that's just as important as where you did, by the way. And what I did was, and I still can't quite believe I did this, but I had, we had drafting departments that would help you with things. And we had to do everything by hand those days, draw the contour maps and cross sections. I had her put a dot on every producing well. And the oil is produced from strata that are at different depths. And what I had her do was choose, depending on the strata that it was producing from, do it with a different color. Because, if you had all the wells, it would just be this massive stuff. But when you do that, what you start to see is you can, I don't know how well it's showing up, but you can sort of see some stripes of red across the top. Those are beach sands, okay? So, and it wouldn't show up so well, especially the one that's in the massive purple in here, which is a limestone layer, which is more massive, if it weren't for the fact that I'd done that in a different color. And and the whole key of of finding oil is to figure out a way to look at the data that nobody else has thought of so that you can figure out where the oil is. That was the whole game. And it was actually really, really fascinating and really, really fun. And actually, this is the other thing. This is a three-dimensional issue too, because each well, we would basically, after you drilled it, you get all of these logs. You lower an instrument down, and this is, I think, some kind of, you get things like a measurement of the resistance of the formation. If there's oil that has a different resistivity than the salt water that's in the pore spaces otherwise, and you can see all sorts of other things as well. So we also had to sort of look at this in a three-dimensional way. Since then, I did go into environmental consulting as well, and then ended up transitioning into education and did high school teaching for about 7 years. And these are actually some of my students on the left. And that was great. It was I'm really glad I had that experience. And then I was hired by EDC to write an earth science curriculum, a high school earth science course called EDC Earth Science. And I've been at EDC for about 8 years. So I have a varied background, but it's full of data. And now you have a sense of what my perspective is. So the Oceans of Data Institute, we see ourselves as addressing a really critical and urgent need. One of my colleagues who's been working with me on creating the Institute and leading the Institute is Kim Castens. And this is a quote from her: "Students need to learn to use data to solve real problems. Data can't be on the sidelines anymore." So why an institute? Well, first of all, data skills are more important than ever. I mean, I don't have to say that to you because that's why you're here. we think the place to teach new ways of working with data is the STEM classroom. Okay, STEM means science, technology, engineering, and math, okay? That's where it needs to be. EDC has that track record of getting right out in front of things and pushing the envelope. They're not afraid to do this. And we've got the resources, we've got this amazing staff to make this happen. And I just met, in fact, with our board of trustees last week. And you know, the thing is that everyone I've talked to at EDC about this, and especially some key people who've put such energy into making this happen. You know, it's been many other people other than me who have made this institute come into being. And I realized it when I really started looking into the history of EDC, that this is what EDC does. So this is our vision. Now, one of the first people to contact me was someone named Kirk Bourne, who's a professor in astrophysics at George Mason University. When we did sort of a soft launch, just a press release with a very simple website. Until today, we launched a new one in July. And he was so excited about what we were doing, and he's involved in the Large Synoptic Survey Telescope project. Now, this is a $400 million NSF, National Science Foundation, funded project that is in the president's budget right now. And when I was Googling it the other day, I immediately found this headline in Quantum magazine about the LSST, calling it and saying it a digital copy of the universe encrypted. I mean, think about that. That's unbelievable. I mean, think about what that means. But it's not going to mean anything unless we figure out how to make sense of it. Otherwise, it's just data, you know? And what we see is, and what got me so excited about this, is we see big data transforming how we learn about the natural world. So in these pictures you see on the upper left, those are the tracks of marine animals, marine predators, that were taken using satellite tags over a 10-year period of the Census of Marine Life. And so that's one set of data that's represented here. This is, let's see, it's a map of the human X chromosome, although part of it I think is missing off the bottom. We have the Kepler telescope has been taking incredible, pictures of the cosmos, looking for exoplanets. And then, this is the Keeling curve of atmospheric carbon dioxide. I'm already working on projects that engage pre-college students in all of these things. I'll be talking about one that uses the animal tracking data a little bit later. I worked on a project for about 3 years with the Harvard-Smithsonian Center for Astrophysics, where we had everything from 7th graders through AP physics students taking images via their computer with a telescope of stars, analyzing the light, the brightness of the light of that star, combining it with the data that other students had collected, and detecting planets orbiting other stars. I mean, real planets orbiting other stars. It was incredible. It was really incredible. I'm working on a project with SRI International near Stanford, associated with Stanford, which is bringing the NASA's Giovanni data to students. And this basically is all sorts of atmospheric and land and ocean data related to climate. And I've seen in classes teachers, having the kids make predictions about what is the seasonal precipitation pattern going to be for this country in Africa that we studied, and then after they do it, just calling up in real time, a time series showing what it is, and is this what we expected or not in real time, just communicating directly with the computers at NASA. It's pretty incredible. So here's the challenge. So here's the challenge. We need a better system for big data education. And we have a critical need for data scientists. We need to have an empowered citizenry, a citizenry even beyond those who might work in data science, who know how to access this incredible resource to make smart decisions about things. It's important to start young. And this brings such incredible opportunities for learning beyond what was ever possible before in the classroom. And this is a quote actually from the conference goals for this that somebody wrote, which I thought was great. Given the broad reach of big data and analytics, the need for skills training encompasses basic understanding that begins in K through 12, deepens during baccalaureate and postgraduate education, and continues through ongoing education during one's professional career. So how does this fit into high school education? Well, you know, there's state assessments and AP exams and national standards and state standards and SATs and back to basics. And I think elective courses, they're great, but they tend to get crowded out. Anybody who's had anything to do with a high school, whether they've had a kid in high school or they've been in high school recently or whatever, knows that elective courses tend to get crowded out. So we think that this needs to be front and center part of the core curriculum that students take. But students right now have limited contact with real data in high school. Despite how data-intensive scientific work is, like these are the statistics for an earth science textbook, and it's mostly artist renderings and photos and so forth. Very little work with actual real data in any form. Most classroom experiences are with small student-collected data sets. And that's great, and it's important. As you said, any kind of work with data is interesting and important, but it's not enough. And I think even some of the most, it's only one step in the process. And I think, you know, even the most sort of cutting-edge pre-college programs tend to focus on students, you know, getting out and collecting data in a river or a stream or whatever, or weather data or whatever. And you know, teachers are so cramped on time in the classroom that if they do that, the furthest they usually get is to the data collection phase, through the data collection phase, and they very, very rarely spend any time actually thinking about the data and making meaning from it. So we need to sort of move kids beyond just the collecting the data, although that's important to understand, and give them time actually making meaning of the data, thinking about it. The other thing, and this is a critical limitation, most high school teachers have limited, or pre-college teachers have limited experience working with large data sets themselves. They haven't in a science class. Typically, high school teachers have not done scientific research themselves. And so they don't understand, and there's so much, especially when you're working with unstructured data sets, real data sets, you don't quite know what you're gonna see. So there's a lot of on-the-spot, you know, work that needs to be done and decisions need to be made in order to support students when the unexpected comes up and to know how to guide them in understanding how to work with data. But the landscape's shifting, and it's hopeful. There are some new national science standards released just this summer that require students to work with data. And these are some statistics that basically show, now the last set of national science standards, data was barely mentioned. In this one, it's close to 50% of the standards mention data in one way, shape, or form. And so this is a really positive thing. There's also a very strong emphasis on scientific practices. In fact, the content is supposed to be taught entirely in the context of scientific practices. And these are the scientific practices that are emphasized. And I have just 3 of them highlighted: developing and using models, analyzing and interpreting data, and engaging in argument from evidence. But really, I could have highlighted all of them because all of them are part of the process of working with data. So there's hope, and there's going to be some pressure in that direction. We just have to help make sure that it happens in the right way. There also are, you've probably heard of the Common Core standards. They've been in the news a lot lately, that focus primarily on English or reading and math. And they also have measurements and data and statistics and probability in the standards. So the Oceans of Data Institute, this is what we're doing. Basically, we think actually a really critical part of everything is especially at the beginning, our meetings like this, where we get stakeholders together, we talk about things, we learn from each other, and we find the best pathway forward. So that's one of the things that we want to do, is to help sort of bring people together and facilitate conversations and so forth to move things forward. there's a lot of research that needs to be done to know how to do this right, how to teach students, and I'll talk about that a little bit. And then we need to actually get things into the classroom. We need to develop and test tools and educational materials and get them into the classroom. So we're working on all three of those things. Now this is what we're doing along the lines of research, and we hypothesize that there's this sort of learning progression. And if you start with unstructured observations with the human senses, and then, the next step would sort of be students working with small student-collected data sets. That's another important step in the process. Then you move on to professionally collected large data sets, maybe with well-structured problems, and ultimately to professionally collected large data sets with ill-structured problems. And we can hypothesize that there are those stages, but we really don't understand the transition between them. What needs to happen with a student, and how do we transition them from one step to another? So that really needs to be researched. And this is what we're trying to do. We're trying to move students from embodied experiential grasp of their natural setting and data collection methods to metadata. We're trying to move them from dozens of data points to megabytes. We're trying to move them from simple and transparent tools and techniques to sophisticated tools and techniques. And we're trying to move them from common sense lines of reasoning to spatial, temporal, statistical reasoning and multi-step chains of reasoning. And, and it's not even multi-step. We have a natural tendency to always think in terms of linear chains of causality, and that's not really how it works. There are multiple influences on things when you're talking about complex data. So Intellectual Hub, what are we doing? The scientific community is working very hard to organize itself, to make its combine their data in it, get it into digital form and combine it. And the geoscience community is no exception to that. The EarthQ program is a National Science Foundation funded program that is going through the very hard process of getting, geoscientists who vary a lot from the geoscientist who's out in the field with his hammer collecting, his or her hammer collecting data and rocks and bringing them back and have their data in file boxes and things like that, to the folks who for example, meteorologists and so forth, who tend to be on the other end of the spectrum where they're working with sophisticated climate models and so forth, and tend to have a lot more digital data that they're working with. They're trying to bring all of them together to basically make the data commonly available to all of them. And so, and while this is happening in different scientific disciplines, those of us who are involved in education need to work very hard to have our voice in the mix, saying, make this data accessible to students. Make it accessible to novices, because this is the pipeline that's going to figure out what to do with that data about the universe. This is the pipeline of people that we need to be educating, and we can't do it if the data isn't accessible. So we had a workshop. We co-convened a workshop funded by NSF out of the Scripps Institution of Oceanography, bringing together faculty from many different universities, research institutions, and data providers and so forth, talking about this. What's needed to bring data into the classroom. I also was involved in a very interesting project, again funded by NSF, called the Oceans of Data Project. We sort of borrowed the name for the institute, but it's not just about the ocean, folks. Okay, don't go away with that impression. Where we realized that we wanted to make these data accessible to students. And when we started looking around the web and looking at the literature about, big data and students and getting data into the classroom, we found that there wasn't that much directly about that. There was a lot of knowledge out there relevant to that, but there wasn't much directly about that. So NSF funded us for a 2-year exploratory project to basically go out and gather that knowledge. And we pulled it together into, it was a fascinating study. We also brought experts together and had some fantastic conversations. And we put together guidelines with the key underpinnings, cross-cutting guidelines, and over 70 specific guidelines for designing educational interfaces to large complex databases. And so I have a couple of copies of that with me. If anybody's interested in it, I can show it to you, or you can download it from our website. But we found that there's been a lot of interest in this. NOAA and NASA and Ocean Networks Canada and various other everything up to UNESCO have asked us for copies of it and have said that they found it very useful. So that's another thing that we're trying to do, is pull together those shards of expertise and knowledge that are relevant and put them in a place where everybody can use them and in a way that everybody can use them. In developing and testing, I'm going to talk about one particular project that we're working on right now. And this is one that, and in fact, I was just in the classroom last week as they were, because we're piloting it. We did a pilot in the spring, and we're doing another pilot now. We have the development site on track right now, and this is what I'm going to be showing you. This is Ocean Tracks Investigating Marine Migrations in a Changing Ocean. And I'm going to talk about this not so much because I want you to think about this kind of data, but I want you to think of this kind of data as a metaphor, as an example of the kind of thing that we could be doing with students to help raise their data using skills. Now, basically the approach, this follows our guidelines from the Visualizing Oceans of Data project. And what we're doing is, our focus is on automating processes that are not important to the learning goals. So in this case, we're trying to get students to the meaning making with the data. So they could easily spend all of their time plotting the tracks of marine animals, and that would be it. And then they go on to the next unit that they have to cover. But we didn't want them to do that. We want them to think about making meaning of the data. And so we automated the process of getting them to the data. Minimize distracting information. Now, when you're learning new things, you do that with your short-term memory, which is effectively whatever you can hold in your attention at any particular time. And when you get to be more of an expert, you have what we call schema or mental models that you can build on, so you can handle more. But when you're first starting out, you don't have a lot to work with. And so if you have distracting information, then it ends up taking away from what you can learn. So you want to there's this sort of general principle of you want to take out the distracting information and make what's important stand out. And then we found that it's very important, the curriculum and the guidance that you give them, it's not enough to just get the data to them. You have to guide them on how to use it through some sort of process that we're still figuring out, of guided investigations that increase their use of the data and the sophistication of what they do over time. So what we have is, this is the interface. It's on Google Earth. And you can see these are the tracks of the red are elephant seals, and the blue are great white sharks that they've tagged with these electronic tags. And students can very quickly turn on and off the tracks of individual animals, also bluefin tuna and albatross. Or they could turn them all on, they could turn individual ones on, and so forth. And in this case, you can see that the elephant seals are a different color than the great white sharks. They immediately can start looking at this and noticing patterns and asking questions like, what are all the great white sharks doing down in that area down there, which they actually call the White Shark Cafe. And actually, the researchers don't actually know why they hang out there yet. They're still trying to figure that out. So, but anyhow, and it's part of our thinking is that this is data that the students can relate to. You're talking about animal behavior. You can sort of think about, okay, so we could follow our tracks around, and would it tell us instantly, if you just had our track, would it tell somebody instantly why we were going there? No, you'd have to use indirect methods, and you have to think about other things and collect other kinds of data to figure it out. We allow them to easily create and interact with the data display. So we have a tool where they can look at, this is just one of the elephant seal tracks. And you can see that we have this graph slider, and this is displaying the speed of the interval that's highlighted on the track over that interval. And you can see at some periods, like whether it's up near Alaska there, it's actually moving more slowly right on the left-hand side there. And other periods when it's more traveling, it's going faster. You can also look at the depth, because elephant seals dive. You can look at the depth of their deepest dive each day. You can look at the curviness of the track and other things like sea surface temperature and chlorophyll along the track. And they can actually also superimpose layers that show sea surface temperature and chlorophyll, which are time coordinated with the sections of the tracks that they're studying. And then we provide for them tools. We're working on this project, I should have mentioned, with Stanford's Hopkins Marine Lab and also with Earth and Sea, which has been an amazing software development company. They've just done incredible things. They've been right in there in the classroom with the students seeing how things are working, which I think is so important. So we're providing them with tools that they're the same tools that scientists are using. So we're not making up anything. This is all real, but we're making it so it's easy for the students to do. So here they've turned on all of the elephant seal and the great white shark tracks, and they've used this hotspot tool to basically create a heat map that shows where the largest number of animals are spending the largest amount of time. And then they can from there start, anyways, I'll get to the curriculum in a minute. I'm getting ahead of myself. So then we've done like 2 different versions of curriculum to go with this to help students use this. And what we found is the first time we gave them these step-by-step instructions and we focused them on that one elephant seal track, and we said we really want them to know what it is you can do, all the things you can learn from a track. And we figured that would take them 3 days, and then they move on to the next one, the next one, the next one. It took them like 3 weeks to look, and they were still looking at one track. So I said, okay, this isn't exactly going at the pace we thought it would. And so we said we need to get them into more of the tracks and more of the data earlier on. So this time we have this modular approach where we start out with some challenges that get them to look at all of the data and get them to use the tools, and they try to figure out which animal traveled the longest distance overall and per day, and which animal traveled the fastest speed. So they look at all the species and they look at all of the data and they figure this out. Then we move on to ask them to make inferences based on indirect evidence. So where are the prey of the elephant seals likely to be found? And last year we did a survey of the students at the end of the unit, and we said, what would you like to learn more about if you used ocean tracks some more? And a surprising number of them said that they would like to learn more about squid and seahorses. And of course, it's really hard to put a satellite tag on a seahorse. But it's a good example. So this year what we did was we have them develop a map, a prey map of where the prey is, because that's the whole point. That's why they tag the predators, is because if you know where the predators are, then you can infer where the prey is and where the healthy ecosystems are. So, and then you want to give them opportunities to draw evidence-based conclusions from this complex data. And so we challenge them to locate a diversity hotspot in the Pacific Ocean, which involves maybe using the hotspot tool, understanding why there seems to be a hotspot there, looking at the chlorophyll map, looking at all sorts of data, and the students sort of pull together what may be, what we're finding is the students have different ideas about where the diversity hotspots are, and then they debate it, and they say what their evidence is and so forth, and it's kind of cool. And this is really important to students, to relate the data to real-world problems. So they see how important it is that the animals seem to be hanging out in the transition zone, for example, between warm and cooler water. I mean, that's where the fishermen are. They're right on those frontal zones. And then when you realize that the ocean is changing, the temperature of the ocean is changing in different ways, that this is why it's important. These animals, they rely on this. And what does that mean for the animals? So there actually are some really important questions that the students can explore that are the same reasons the scientists are exploring these data. So what are we learning? Well, we're seeing positive signs that simplifying the process, automating certain processes and doing this is actually allowing the students to focus on making meaning of the data. We need to overcome some technology deficiencies. One of the things we're seeing, we worked with 3 pilot teachers very intensively in the spring. We worked with the same 3 in the fall. The technology they were using changed between the spring and the fall. One of them in the spring, it was all English as a second language learners, which was a challenge in itself, but they had these old computers with terrible resolution that they were dealing with. And these poor kids that were bringing in their own laptops to work with. So then you got all kinds of technology, all kinds of different kinds of technology. And then this year they have Google Chromebooks. Other classes went from having having regular laptops to having, iPads and things like that. So, and the teachers are scrambling around trying to catch up with this. And then, even things like, the associated software that they might use where they keep, records of things like Google Docs or things like that, the teachers are just learning about it, and the students don't really know it either. And any kind of, anything that goes on with the technology completely distracts. It can set them back days. So this is something that needs to be worked on. I don't know what the solution is, but it needs to be worked on. It's definitely an issue. And the curricular supports and teacher facilitation are critical. So at the top of our to-do list, all of our to-do list, I think, should be, is defining the skills and understandings that students and teachers need to develop. That means there's a critical need for convenings like this. And I'm really hoping to learn from you a lot more about what it means to be a data scientist and what skills students need. And one of the things that I'm doing here is differentiating a little bit between skills and what we call pervasive understandings about data that students need to develop. And examples of skills that we might put on our list are making data representations using both traditional and computer-based tools, calculating descriptive statistics, using Excel and similar software, reading graphs, tables, maps, and so forth, other data visualizations. Examples of pervasive understandings are just the fact that data are useful for answering questions. Data can be used to make inferences about events that we didn't see. Every data set is incomplete. And a single observation can reflect multiple influences or processes in the real world. And there are many more that we need to define. We don't even know how to assess at this point students' data using proficiency. We don't really know what it is we want them to be able to do specifically enough to have the assessments, the way of measuring their progress. And all of this needs to be figured out. Good signs, we had this really soft launch in July, just one press release, and immediately it generated strong interest from the education community. Several online journals called and interviewed me, and then this rippled around the web, and that's actually one of the reasons I'm here. Steve saw one of these articles, or one of the related articles, one of the echoing articles on the web. And then we also had sign-ups for our mailing list from people, a lot of them schools, not just schools, other nonprofit organizations, industry, and universities, many universities from all of the states that are in dark blue, and Hawaii and Australia and Europe, and even there was somebody from Rwanda who signed up. So there's broad interest in what we're doing. And then that's all I have to say. I want to thank you very much. And please look at our website. We just launched it today. And so it has a lot more information about some of the work that we're involved with. Great.